As we begin this part, you can see that at least the appearance of our integral looks much more complicated because it has a square root in it. Now, we've been relying on knowing how to integrate u to the nth with respect to u. That's what we've been relying on. We know that that's 1 over n plus 1 times u to the n plus 1 plus our constant of integration, kind of squeezing it in there. Now, there's nothing in the rule for integrating a power of u that says u has to be a positive integer. We've dealt with u's being, exponents being fractions and even being negative integers or negative fractions. So I think that we can apply the same type of substitution that we've been doing in the past, but not worrying about it being something in parentheses. We could have a radical. So that might lead us to believe that when we're trying to integrate something like we see here, let's go through this, the integral of 2x cubed times the square root of 3x to the 4th plus 10 with respect to x, that it might be very reasonable to replace what is underneath the square root with a u. So we'll let u be 3x to the 4th plus 10. Now, what happens then is we have the integral of 2x cubed times the square root of u dx. Now, that square root of u can be written as a power of 1/2, and so we're getting to this. What we're trying to accomplish is getting the integral of u to a power with respect to u. So we're one step closer when we think of it in this fashion. Now we've seen the idea that if we have some extra constant factors hanging around like this 2, that we kind of like to get them out of the way so we don't have to think about them so much. So I'm going to factor that 2 out, and then I'm going to arrange things so I have my u's together, my x's together. So I'm going to write this as u to the 1/2 power times x cubed with respect to x. That's the integral we're going to work on. And now we're hoping to replace x cubed dx with a du, or something about du. So we come back over here to where we named u, and we recognize that if u is 3x to the 4th plus 10, then du is the derivative of u times dx. Well, the derivative of u is 12x cubed, and times dx, don't forget. Okay, so what that means is that we're trying to replace x cubed dx, and so we're looking over here at the x cubed dx, and we need to solve for it. And we can easily solve for it by multiplying both sides by 1/12. And so we have x cubed dx is 1/12 du, so we'll put that value right there, of course. So now our integral becomes 2 times the integral of u to the power 1/2 times 1/12 du. Now, the next thing we'll do is we'll factor that 1/12 out. So we have 2 times 1/12 times the integral of u to the 1/2 with respect to u. And of course the 2 times 1/12 is 1/6. And now we're ready to integrate u to the 1/2. Well, we have to increase the exponent by 1, and when we do, we get what? 1.5 or 3/2. So we have an exponent of 3/2. We have to multiply with the reciprocal of that exponent, which is 2/3, isn't it? Plus our constant of integration. And then we simplify this completely. We have, of course, 1/6 times 2/3 would be what? 2 over 18. And u is, what is u? It's 3x to the 4th plus 10, and that has a power of 3 over 2 on it. And I guess we better reduce 2 over 18 to 1/9. And so our answer is 1/9 times the quantity 3x to the 4th plus 10 raised to the power 3 over 2 plus our constant of integration. And that would give us the correct result here. Now, so we can deal with integrals of things that are square roots or cube roots or fourth roots, if it's an appropriate problem, of course, and we're going to make the substitution for u what is under the square root or the cube root or so on. Now I'd like to pause here for a moment and kind of remind you of where we've been, so this is going to make a little bit of sense in the future. Hold on just a moment. Well, as you can see here, I've written down, I think all 5 of the examples that we were asked to do. And I want you, if you haven't already, I want you to notice something. So when we're talking about this first integral, we made the substitution u is equal to x squared minus 1, and we found out that du is 2x dx, and that matched exactly what we have here. Okay, so that was a quick idea that probably was going to work. Likewise, when we looked at this one, we made a substitution u is 4x squared plus 5, and our du ended up being 8x dx, and here's, of course, the 8x, and here's the dx, so that was important. Now, when we look at this next one, okay, we made the u substitution of 3x plus 4, and our du ended up being 3 dx, and we didn't have a 3 at all. Now, let me do one more, and then I'll point out what I'm wanting you to notice. In this fourth example, our u was inside those parentheses, 2x to the fourth plus 7, and our du was 8x cubed dx. And of course, we had a 5x cubed dx. Now, here's what I want you to notice, the important part. When we're making this substitution, the part for us to really recognize is, do we have, when we find du, do we have not the exact result, do we have the right power of x? See, and in this first example, besides the 2, besides it being exact, our du was x dx, and we have an x dx. In the second one, our du was 8x dx, but it's important to recognize it's the x to the first power dx. And here's our x to the first power, and there's our dx. Now, in the third example, we didn't have a power of x at all. So what I'm telling you is, more or less, we don't care about the constant, because we can adjust the constant. But we do care that we have the right power of x. And so in this case, du doesn't have any x's in it, does it? It's just a constant times dx. And our original problem didn't have any extra x's. That was important. Okay, here, there weren't any x's outside those parentheses. Now, when we look at this example, the x's we have outside the parentheses is this x cubed. So when we choose u, du better give us stuff about x cubed, and in fact it does. If it didn't, we would be in trouble. So this kind of gives you an idea of what you might choose to be your u. See, it makes reasonable sense then, besides we've already done the problem, that if I let u be what's inside the parentheses, the derivative of that's going to create an x cubed. And so we know when we find du, we're going to end up with something that has x cubed in it. And that's all important to us to make sure that we're making a good substitution, a valid substitution. We still have to work out the details, but that gives us a hint on what we might try. Okay, let's, now we've seen that we can use radicals. We can find integrals of radicals because we can make the u what's under the radical, and then we have an exponent on it that is a fraction. Let's talk about what would happen if we had negative exponents. That would mean that we have, actually, we're integrating things that are fractions. Let's look at the next page for the example 6. Oh, okay, they get more and more complicated looking, don't they? Here we're to find the integral of the fraction 6x squared over 2x cubed plus 1 raised to the 4th power with respect to x. Now, I see parentheses with a power on it, and so that makes me think of a u substitution. So before I even get started, let me rewrite the problem. Okay, the integral of the fraction 6x squared divided by 2x cubed plus 1 raised to the 4th power with respect to x. Now, I see that parentheses in the denominator with an exponent on it. And so that leads me to believe that maybe if I replaced 2x cubed plus 1 with a u, I would have u to a power. Now, it'd be in the denominator, obviously, but it would certainly be u to a power, and I can adjust that. So let's stop and think about, well, if I make that replacement, am I going to have the other stuff I need? And we can see right here that du is going to be actually what? 6x squared dx. And I see a 6x squared. What's really important is the x squared. But I certainly see a 6x squared unrelated to the u that I've got down below, right? And so I'm thinking this is probably going to work. So we start out by making appropriately the substitution. That is, we're going to replace 2x cubed plus 1 with u. And so it ends up being a fraction that looks like this. And then we have to just know a little bit of algebra, and we all do. We can rewrite 6x squared over u to the 4th as 1 over u to the 4th times 6x squared, and then, of course, dx. And now we see, oh, it's so nice because this entire 6x squared dx can be replaced with du. So this is actually a little easier than what we've been doing. So this is the integral of 1 over u to the 4th. We make our replacement and we replace 6x squared dx with just a du. And then we see that, oh, well, we can't integrate that directly, but we can write 1 over u to the 4th as u to the negative 4. And so now we're in a position that we can see that we'll be able to complete this. To integrate u to the negative 4, what do we need to do? We need to add 1 to the exponent. So let's see, negative 4 plus 1, oh, that's negative 3, isn't it? So we have a power of negative 3, and we offset that by the reciprocal of that power. So that would be negative 1/3, wouldn't it? 1 over negative 3 plus our constant of integration. And so this ends up being a negative 1/3 times our u value, which is 2x cubed plus 1, with a negative 3 power on that, plus our constant of integration. And then we need to do a little algebra to clean this up. Remember, a power of negative 3 means that we have 1 over 2x cubed plus 1 to the positive 3 power. And then we could multiply those two fractions together. A negative 1 times a positive 1, or we can just say a negative times a positive, would have a negative fraction. And in the denominator, we had the 3 in the first denominator times the 2x cubed plus 1 to the power 3 of the second denominator. So there would be our final answer. So this substitution is kind of now moving over to where we can also deal with fractions, and certainly fractions that have powers in their denominator, that is, parentheses with powers in the denominator. Let's go to the next page for example 7. Well, I want to end this part with 2 more examples, example 7 and example 8, and they each have a little twist to what we've been doing. It's very similar to what we've been doing, but they're just a little twist. So let's begin this problem. Let me rewrite so that we can have a place to do our work. We have the integral of a fraction. The numerator is x plus 1. The denominator is 4x squared plus 8x in parentheses raised to the power 3. Now, if things go as we have been doing, because we have parentheses and a power of 3, it's reasonable for us to believe that we're going to replace 4x squared plus 8x with a u. That's going to be our substitution. Now, there's a little difference this time. Okay, let's go ahead and write this out then. That means our integral would be the integral of x plus 1 over u cubed with respect to x. Now, when we rearrange this, then we would have the integral of, and let's say 1 over u cubed, and then we would have to multiply it with the top. And so that actually needs to be in parentheses, otherwise it just really looked like we're multiplying it with x, wouldn't it? So that's the form we have now. And this is, of course, this is much different than we've had before because we've never had x's that had an addition in them left over, did we? Well, when we come back over here and look at this u, and we want to know how we're going to replace, see, what we're going to have to do is replace x plus 1 dx, x plus 1 times a dx, aren't we? And the only tool we have is to go back to du and say, okay, well, du is the derivative of 4x squared plus 8x times dx. Well, now this time, the derivative of 4x squared plus 8x, the derivative of 4x squared is 8x, plus the derivative of 8x is just 8, and that's what gets multiplied with dx, isn't it? It's the derivative times dx. Now, this looks different, and you know, what's important here, though, is to see that what we have left over at this position has x to the first power plus a constant. And what we have in here has x to the first power plus a constant. In fact, if we'll notice here, 8 is a common factor. So we can actually factor 8 out of on this right-hand side, and we'll have 8 times x plus 1 times a dx. And then it begins to sink in for us. Here's x plus 1 times dx, and here's x plus 1 times dx. So we need to solve for this. We'll multiply both sides by 1/8. So 1/8 times du is the x plus 1 times dx that we're looking for. So we can replace x plus 1 dx with 1/8 du. So it ends up being the integral of 1 over u cubed times 1/8 du. Now we're going to do a couple of things at once here. We're going to factor out the constant factor 1/8, and we're going to write 1 over u cubed as u to the negative 3, and of course we still have our du. And so now we're ready to integrate. Here's our 1/8. When we increase the exponent of negative 3 by 1, we end up with an exponent of negative 2. And we have to multiply by the reciprocal of negative 2, which is negative 1/2, plus our constant of integration. So we end up with negative 1 over 16 times u to the negative 2 power. And u is 4x squared plus 8x. And that has a negative 2 power on it. So our plus our constant of integration. And then lastly, we'll write this as one fraction. The negative of the fraction will have 1 in the numerator, 16 in the denominator, and when we change that exponent to change it from a negative 2 exponent to positive 2 means we put that in the denominator, don't we? So plus our constant of integration. And there's the result. So that was a little bit different twist because we had a strange looking du, didn't we? Okay, here's example 8. And it has a little twist to it as well. And we're not going to see this happen very often, but it does have this twist. So here we're supposed to find the integral. We'll say the integral of x times the square root of 2x minus 7 with respect to x. Actually, maybe I've made that more difficult than I should. Well, I've made it more difficult than I should, but we'll stick with this one. Well, we've seen things with square roots before, and I went through a long, several examples ago, I went through a long idea about how we would guess whether our substitution is reasonable. I'll tell you what, let me make this, let me make that 2x minus 1 instead of 2x minus 7 under the radical. Still probably a little more difficult than I want, but that's all right. We can manage this. Now, remember what I said before, that it's kind of a good idea to decide whether our substitution is reasonable. And the way we are making the decision on whether that substitution is reasonable is that when we find du, that we have the correct powers of x that are outside the parentheses or outside the radical or outside the denominator or whatever. In this case, if we make u what's underneath the radical, 2x minus 1, we end up with du actually being 2 dx, and we have x outside the radical, and we have no x's at all in our du. And so that seems to lead us to believe that this substitution is not a good substitution. And normally that would be the case. But in this particular example, we can get ourselves out of the problem. So here's what I want you to recognize, that in this case, we've got an x in our integral, and we replaced 2x minus 1 with a u, so we have the square root of u, and then we have a dx. Now the problem over here, see, the problem here is we don't have a way to replace x. What we could do is we could solve for dx and get a du. See, 1/2 du is what dx is. And so when we come back over here, we would have the integral of x times the square root of u, and then we could put a 1/2 du in the place of dx. And then we could factor that 1/2 all the way out, okay, because it's just a constant factor. So we have now x times the square root of u du, which is still a problem because of our x. We need to get everything in terms of u. So this is the reason this one's okay, and it's because we happen to have just powers of 1 everywhere. We could take what we have up here, and we could solve for x so it would be in terms of u. See, in this case, we could say, oh, well, look, u plus 1 is equal to 2x. All I did was add 1 to both sides. And then I could say, well, I could divide both sides by 2, and so I'd have u plus 1 over 2 is equal to x. And so now I have a replacement, you see, for x. I could write this as 1/2 times the integral, instead of x, a u plus 1 over 2 times the square root of u du. Now I have everything in terms of u. Now, one thing, I may run out of room here, I apologize. Okay, one thing that we could do here is we see that we've got this 1/2 underneath inside the integration sign. See, u plus 1 over 2 is really 1/2 times u plus 1, isn't it? So I could have thought of that as a 1/2 times u plus 1, so I'm going to factor out that 1/2 as well as the 1/2 I did before. And so then I just have a u plus 1 times the square root of u du. And it still looks like a problem, okay? But we can overcome the problem. Let's write this as a 1/4 by thinking of the square root of u as u to the power 1/2. And then I could multiply those u's out, couldn't I? See, then I would have, I apologize for having to go to the side here, but I'm turning my paper on the side and I'm going to continue up above or over here. So here's what I've got. I've got 1/4 times the integral of, now I'm going to multiply that u to the 1/2 times the u plus 1. And when I multiply u to the 1/2 times the u, I get u to the, what do? We add the exponents. So the exponent 1 plus the exponent 1/2 is the exponent 3/2. And then plus 1, a u to the 1/2 times 1, which is just u to the 1/2. Okay, so that's the result I have by multiplying those u's out. Oops, except it's du, not dx, isn't it? And so now I'm in a position, okay, I've got this 1/4 outside. Now this is a little tricky too, because this integral is going to give me more than one piece, and 1/4 is going to multiply all of that, isn't it? So I'm putting my result of the integral in these brackets. Now when I find the integral of u to the 3/2 power, I have to add 1 to that exponent, which gives me a 5/2. But I have to have the reciprocal of that in front. Then when I take the integral of u to the 1/2, I have to add 1 to that exponent, and so that'll give me an exponent of 3/2. And of course I have to offset that with the reciprocal of that exponent in front. And then there's plus our constant of integration. Well, I'm really sorry that this is getting so out of hand here. Now I'm going to multiply that 1/4 through, okay? And so I have 1/4 times 2/5. Won't that be 1/10? See, that would be 2 over 20, won't it? So it'd be 1/10 times u to the 5/2 power. And then I have 1/4 times 2/3, which would be 2 over 12, which is 1/6, isn't it? So then I have 1/6 times u to the power 3/2, plus our constant integration. And then we'd finish this off by putting back the value of u, which was 2x, what, 2x minus 1? So it's 1/10 times 2x minus 1 to the power 5/2, plus 1/6 times, instead of u, 2x minus 1 to the power 3/2, plus our constant of integration. So although I ran out of room and got a little messy there, this problem was doable. It was just kind of a big twist from what we've done before. Well, this ends this part, and we're going to continue with substitution, but now we're going to introduce e to powers and also some things where we have to use the natural logarithm.